So today I've got this Panasonic A5 motor. It's got an absolute encoder on it, 17-bit. This one's multi-turn with a battery, and you can see how we've wired it up here with the blue and the violet, S and S naught, white and black, +5 and ground, and then the battery, red and pink. And there's a Panasonic battery kind of attached to the cable there. So we'll take a look at the Panasonic motor first and set it up with a Copley BEL. I got the stow bypass jumper in here and the Copley serial adapter and a 24-volt supply, so not a lot of voltage, so we won't go very fast today. It's a MSMD 012 S1S. There's an A at the end of this motor, but it's an A5 motor. I found some specification at this www3 Panasonic stuff, so I think this is an obsolete motor. It says it's a 200-volt winding, so maybe we're not going to go very fast with 24 volts today, but you can get all the specky stuff here. It doesn't say very much about the multi-turn other than 17-bit, and if you don't have a battery, then you're not using multi-turn, and you can ignore the battery fault. Let's take a look at the wiring here. So I've got the motor cable folded back, the shield. Make sure the shield goes not to the case of the motor, but all the way back through. I showed the shield connected to frame ground on the drive. I like the XEC for this because it's a higher voltage. I'm going to use a BEL today, but this is the wiring for the XEC. So frame ground, the shield goes to frame ground. I've got +5 volts with a white wire, and I've got signal ground with a black wire. I've got light blue for S and violet for S naught, and they say green yellow for shield. I didn't see that. I just saw a drain wire. Yeah, and the battery hooked up. The plus goes to the plus with red, and the minus goes to the minus with pink. And there's actually a Panasonic part number. It's a lithium 3.6 at 2,000 milliamp hours. So that should last a long time. I think this has been in the cabinet for a couple of years, so still works. No battery fault. So we'll take a look at CME and see if we can do some configuration. So for this motor, it's a brushless rotary motor. It's Panasonic A format. We've got the incremental and the MINAS A, but it's just an absolute A format. And the difference between like the A5 and the A6 is the bit, so 17 bits. And I said 12 bits multi-turn, 4096 is typical. I can't find the spec on it. Could be more, but I just did a typical multi-turn. I'm not ignoring the battery, so there's no battery fault. Never ignore your feedback. If you have a break, you can come to a controlled stop, and I just put it in a network mode. You can emulate the incremental count out and divide it down if you have to, but it's 131072 counts per rev, so not so bad. And for the motor data, Panasonic, I said MINAS A5. There's the model number. I got an A at the end of that model number. It's an 8-pole. The inertia, 0.015 kilograms centimeters squared. It's a small motor, so it doesn't have a big inertia, and that looks right. I found that on the web page. Peak torque, continuous torque. The continuous torque was on the motor, 0.32, and the current was 1.1 amps, and A is for RMS with Panasonic. So you can divide 0.32 by 1.1 amps and come up with 0.92 amps Newton meters per amp RMS, or 0.205 Newton meters per amp peak, which would be the same for the volts per radians per second, 0.2 0.051. Just make these two numbers the same, and then you can see the volts per kRPM. 21 volts per 1,000 RPM. So with 24 volts, I should get about 1,000 RPM. 24 volts. I have a lot of resistance, so there's some IR drop. I measured that resistance. Just use an ohm meter, and I set the inductance to half. It's approximately right because the calculated values came out okay. You can save this to a motor data file, and I'll do that. So I'm just going to save it, and I'll just go A5 Abs. Then I calculated the initial tuning parameters, and you see the current limits. This is amps peak, not amps RMS, so 1.1 amps A is for RMS, so multiply that by the square root of 2. Simple math. And we can check the, be sure to save. So these are the calculated values. And so this is the current loop tuning. Should be about a kilohertz. 600 hertz, it's a little low. We'll do our own tuning. There's the current limit. It's not 1.1 amps peak. It's 1.56 because it's 1.1 times the square root of 2. And there's the peak current. So let's take a look at the current loop tuning. So apply to the current loop. Auto setup checkbox. Hit start. Gains tab. So we want to look for some ringing. There's some ringing. Cut it in half. And nice round numbers. So I'm going to look for some integral windup. There's some integral windup. Cut it in half. Current loop's done. Save the flash. So this motor can do 6,000 RPM. I've only got 24 volts. So on the V loop, we could say 6,000. We're not going to go that fast. It's a warning, just saying, hey, you can't do that. But these are the calculated gain values for the velocity loop. So we're going to tune the velocity loop here. Go to velocity, auto setup checkbox. I'm going to knock the velocity limit down a little bit. If you have a load, you really got to knock this down. But I like to do this no load first. So 600 RPM is 10% of the. I'm going to slow it down just a little bit here because I'm worried about hitting the velocity limit, especially if I have some current. So I'm going to monitor the current, actual current. Okay, record, and the gain. So start off with 600. When the gain's too high, it breaks into oscillations. I keep break into oscillations, cut the gain in half. That's an oscillation. You can hear it. There's a little bit of ringing going on here, but the motor shaft is back and forth moving. So I'm gonna move the pole out a little bit. If you have a large inertia, you might want to make it less bandwidth. Just going to try to get that. You can see the ringing a little bit at 200 hertz or slightly before 200 hertz. That may be a little high. Cut it in half again. It's a little subjective here. So you could go a little higher. And just going to guess at 60 here. When the integrator is too high, you'll get some integrator wind up. See what that looks like. Oh, that's pretty good. There's a little bit of it. Yeah, there's the integral wind up. Yeah. We can come back to this when we do a position move. That'll affect the settling time. You gotta press the enter key to get that number to stick. So we're gonna make a position move. 131072. Gains tab, auto setup checkbox. So put the distance in 131072. That's one rev. And trajectory limits, there's no way I can go that fast. We put in 500 RPM. Press start. And I made a single rev. And, oh, there's my integrator. It's if the integrator is too high, you might get an overshoot at the end of the move here. So we'll take a look. Yeah, a little bit of integrator wind up after the move, kind of went above 0. I'm okay with sliding into the position here, so we'll cut that down. If you had a large inertia, you could cut the PP down, 10 to 1 inertia mismatch, put in 100. Following error may get a little bit bigger. If you're done with the current loop, about 1 kilohertz. If you're done with the velocity loop, let's just leave that back. Looking real pretty there. And you can have a little, if you want a little error while you're moving, you can allow error while the move is progressing, and then it slides in. That's exaggerated. There's the default value for the velocity feed forward. I'm going to make a 10 rev move. And I'm going to take a look at the voltage bus, voltage, terminal servo. It's like the back EMF plus the IR drop. Miscellaneous, event warning, limited. So it's 10 revs. I should be able to go 750. Do a little slightly longer trace time, trying to capture all that at 2.5 seconds. You can see the voltage at 500 was about 10. So let's try doing something we can't do, which is 1,000 RPM. Voltage limited, you saw that? Little warning there. So yeah, constantly voltage limited. The following error grows exponentially. Eventually you'll get a following error fault. That's not good. So let's cut the speed down. We don't want this exponentially growing following error. There, that looks nice. And there's a little ripple while we're moving, but it's plus or minus 50 counts out of 100,000. So that looks pretty good. It's probably the motor detent or something. And again, that's just your basic tuning. You get a good move, you can save that to a file, and we can look at it later. Be sure to save the flash, and at the end of the day, save the CCX file, and just call it Panasonic. BEL, and it's an A5 motor with Abs 17. All right. If you did have any errors for the feedback, you get an encoder fault, or maybe there's a battery fault because the battery's not hooked up, you'd see that here under encoder status. Everything works good. All right, so that's the A5. Thanks for watching.